So Kubernetes 1.25 had a number of important changes, but at this point in time, I think there are two in particular that stand out: the complete removal of pod security policies and the introduction of a new container registry. And the goal for the latter was to have the new registry eventually replace the previous one. That migration has since been expedited. As of March 20th, 2023, all traffic is now being redirected from the old registry to the new one. Those changes can be a lot for teams to deal with because of the dependencies involved. But it's also an opportunity for you to incorporate policy enforcement in your operational lifecycle. For this, you can use projects like OPA Gatekeeper, Tree, Kubernetes, or Kyverno. And these kinds of projects can help teams mitigate risks associated with known threat vectors, as well as deal with changes like the image registry update. In this video, I'm going to focus on policy enforcement as part of your GitOps strategy in order to protect your environments. I'll spend some time on admission control for people that are completely new to the detailed concepts around it. Otherwise, you can feel free to skip ahead to the parts that are most relevant for you. All right. Policy enforcement is especially important when you have an automated change control process like GitOps. With GitOps, the state of your cluster is dependent on the source of truth in a Git or Helm repository. So you want to have the right guardrails in place. Whether you're applying universal security best practices or custom internal policies, you want to make sure that the automated approach of applying Kubernetes resources complies with those specific security standards. Otherwise, your GitOps strategy can easily become an avenue of automating a number of compromises that can go unnoticed in your cluster's environment. Now, given the important change to the container image registry, that will be the focus of my demonstration later on. Specifically, I'll be ensuring that I don't deploy any resources that are dependent on images from the old registry being kh.gcr.io. If you're already familiar with how admission control works and you're just looking for some fleshed out examples that you can start using right away, please follow the link in the description below to our ECAS best practices, where you'll find examples for both OPA Gatekeeper and Kyverno. From a tooling perspective, I'll be using ArgoCD and OPA Gatekeeper. But first, let's talk about admission control. The API server is the main hub in your cluster. All the requests from users or workloads intending to change the cluster state have to go through it. But there are a couple of steps that take place before a request is persisted to the state in the etcd database. The first step is authentication and authorization. Who is the source, and do they have permission to carry out a particular operation? After this, but in the same request flow, you have admission controllers, and they're used to define best practices for your cluster. Examples of this could be ensuring that all pods have resource requests specified, or modifying requests so that every new pod is forced to have an image pool policy set to always, or denying containers that have root access capabilities. And there are two types of admission controllers. You have standard admission controllers and dynamic admission controllers. The standard admission controllers are compiled into the API server and are shipped with the Kubernetes release versions. Pod security policies used to fall into this category. Dynamic admission controllers are not shipped as part of the Kubernetes codebase. Instead, they are accessed using webhooks. So the requests headed to the API server are intercepted so that they can either be validated or mutated via HTTP callbacks. These are the types of admission controllers that can be used for practices like denying images from certain container image registries. And as I've already implied, there are two types of dynamic admission controllers: validating and mutating. The names imply what each of them actually does. Validating admission controllers will intercept the request path using a webhook to verify whether or not a certain object can be created, updated, or deleted before it gets persisted to the cluster state. Mutation admission allows the webhook to actually change the payload of an object in the request to create, update, or delete. Understanding the order of these two is also very important. Mutating admission controllers always run before validating admission controllers. And the reason is you don't want to validate something that you're going to be modifying. So first comes modification and then validation. It's also important to note that you can't use admission controllers to prevent read operations like get, watch, or list. And there are certainly scenarios where you should prevent read operations, but you would have to use something like an authorization module like role-based access control. The authorization step in the request flow occurs after authentication, but before admission. Now let's turn our attention to OPA Gatekeeper. For starters, Gatekeeper performs dynamic admission control by hooking into both the mutating and validating admission webhooks in the API request path. But how does it actually work? To understand that, I'm going to start by explaining the relationship between OPA and Gatekeeper and how it's implemented in the Kubernetes context. To begin with, OPA isn't specific to Kubernetes, but Gatekeeper is a project based on OPA built for Kubernetes. The general OPA architecture consists of an HTTP listener, policy engine, and an in-memory ephemeral database, so OPA doesn't persist any of the policy decisions. And before version 3, Gatekeeper had a different architecture, but I'm going to focus on the newer one, which has OPA embedded inside of it and no longer exposes an accessible API. Also, in this architecture, Gatekeeper allows you to define and enforce policies using the OPA Constraint framework. And this framework has two important components: constraint templates and constraints. Gatekeeper also watches and replicates Kubernetes resources in your cluster into its database. You can modify what Gatekeeper replicates by updating a custom resource called config. But essentially, this allows Gatekeeper to audit your Kubernetes resources and detect policy violations. Personally, this is one of my favorite features of it. Those resources may have crept in before you applied a specific policy or while Gatekeeper was down, but it's a great way of identifying who or what is going against your policies and how exactly they're doing that. All right, now let's talk about these constraint templates and constraints. Constraint templates allow you to define reusable policies, as well as specify parameters that can be passed to them when they're instantiated. When you create a constraint template, Gatekeeper will create a representation of this constraint template in the cluster in the form of a custom resource definition. That's the template. Constraints are then created from the constraint templates and are specifically applied to one or more Kubernetes resource types along with the necessary parameter values. In the demo that I'm going to walk through, I'll cover the source code for a policy that will block unwanted image registries. This will be done using Rego, which is OPA's policy language. Then I'm going to test them locally. And after that, I'll show you how this is translated to the constraint template along with an accompanying constraint. Those changes will then be pushed as part of a feature branch. And when a PR gets created, it will kick off automated tests. If the tests pass, then we'll merge that to the main branch, which is being watched by ArgoCD. ArgoCD will then attempt to reconcile or update the live state to match the desired state. However, if you're deploying constraint templates and constraints to a cluster with Argo, you need to ensure that the synchronization process respects a particular order. Constraint templates need to be deployed first so that they can be compiled and the relevant CRDs get created. Once that's done, then you can instantiate a constraint based on that template. So we can use sync waves in ArgoCD to order the syncing of these resource types. Once that is done, our policy will be in place, and I'm going to check if it's working for both auditing scenarios as well as blocking invalid releases that are being deployed after the policy already exists. All right, I'm going to start by going over this policy and some tests before walking through the constraint template and a constraint. You're not required to have Rego files along with the constraint template and the constraint files. Having both does add some additional management, but in the bigger scheme of things, it's a good practice that can save you time from debugging potential compilation errors in your constraint templates. This way you can do your quality checks both locally and in the CI stage before rolling the policies out to the cluster. So as you can see, I'm checking for violations specific to pods and deployments. This is obviously not exhaustive enough for my particular use case. It should also include cron jobs, daemon sets, replica sets, and the list goes on. But this is primarily aimed at helping you understand the concepts and having something that you can build from. And just remember that you can see more exhaustive examples in our EKS best practice guide. Now let's go through what's happening here. The violation takes the API request as input, as well as a parameter that gets passed to it, which is an array of disallowed or bad registries. This will take the part of the API request that contains the spec data, like the list of containers, and pass that as a parameter to a function along with the list of bad registries. That function will then check every container in the spec and compare it to each registry in the list of bad registries to see if there are any violations. And that function can be found here. And as you can see, those parameters that get passed, we've got our resource object, which will contain the spec with all of the container images along with the list of bad registries, and we loop through each of the registries and compare that to the container images that exist and search for any images that are prefixed with a bad registry. And I carry out the exact same operation with deployments as well, which is what our second violation check does over here. But how do we know that these violation checks work like they should? And that's where unit tests come in. I'm going to run positive and negative tests for both pods and deployments. And as you can see over here, we're going to be running a test called test pod image registry not allowed. So this is to ensure that a pod that has a container image being pulled from the wrong registry actually gets rejected. And down here, I have a positive test, which is making sure that a pod that has an image that is being pulled from the right registry is actually going to be allowed. And I carry out the exact same steps for the deployments as well. Now, let me scroll back to the top and focus on this one. Now, like I said, this is dummy data for a particular pod request. It's pulling an image from the old registry. You'll see kh.gcr.io. And I've also passed down here as a parameter an array of bad registries. All we have this time is the kh.gcr.io, which is relevant for what we are dealing with. It is essentially the list of unwanted sources. And right at the bottom, I execute the same function that is bundled into the same package over here that is part of the violation checks. And this should return true because this pod is pulling an image from a bad registry, and we are testing to see if this is rightly detected. In the next test, as I already alluded to earlier, I'm pulling an image from the new registry. So I specify that my function should not return true, or essentially this should be false because the registry is allowed. And below I have similar unit tests for deployment. I'm now going to run these tests locally to make sure that the policies are working as expected. And to do that, you can either use conf test or OPA. And you can see all 4 tests are passing. Those are the positive and negative tests, both for the pod violations and the deployment violations. Now let's turn our attention to the constraint template. Here I define the custom resource definition that can be created, the input parameters it takes, and the response messaging for detected violations or denials. As you can see, this is called K8 prevent bad image registries. And this is an arbitrary value, so you can update this to whatever you find to be appropriate for your particular use case. Under the annotations, you'll see I'm specifying the sync wave over here, and this is a value that is a key and value pair that are important for ArgoCD. And you heard me mention earlier that we need to control the synchronization order when we're deploying constraint templates and templates. So this is going to make sure that the constraint template gets created first because I've set it with a sync wave value of 1, and the constraint will have a sync wave value of 2, making sure that this one comes first to ensure that it gets compiled correctly and the relevant CRD gets created before the actual constraint. And if I scroll down, you'll see where I'm defining properties that can be passed. And you'll see under here, we've got bad registries, and that is an array of strings. So that's what we can receive as a parameter for this particular CRD. And right at the bottom is my rego policy, which I reviewed previously. So I already walked us through this and we already tested it to make sure it works. And that will save us the headache of trying to guess what exactly is wrong if we run into any compilation errors. Lastly, we have the constraint file over here, and you'll notice that the kind matches the CRD defined in the constraint template. Again, under annotations, I've added a sync wave value higher than the template for ordering purposes. And then under the spec, I choose which K8's resources that this should match to. So this is being applied to pods, deployments, daemon sets, and more. I'm also excluding certain namespaces where I don't want this policy to operate. And lastly is the badge registry array with a value of the old container image registry endpoint. Over here, I have an ArgoCD application resource that deploys the Ingress controller by Nginx, and I've set it to pull images from the old registry, as you can see over here. This is just to demonstrate how the policy enforcement would work in this particular use case. The Ingress controller by Nginx has already been moved over to the new registry. Now, over here is an application that is meant to pull resources from the GitHub repository that will contain the constraint template and the constraint for the image registry policy. However, at this point, those resources do not exist in the main branch. So there are no policies currently running inside of the cluster. Over here is my Ingress controller by Nginx, and you can see all the resources have been deployed. It is healthy, and I'm going to click on this pod over here so you can take a look and see that the image and the other images that are running for this particular application are being pulled from the kh.gcr.io, which isn't what we want. At this point, we have no policies in place, which is why this has been allowed into the cluster environment. Now, what I'm going to do now is head over to the relevant GitHub repository, which contains all of my resources. And first, I just want to show you the main configuration file that is managing how the tests are going to be run in an automated way once a pull request gets created. As you can see over here, this is going to be triggered on a pull request made through to the main branch. And all I'm doing is installing OPA. And once that's done, I'm going to run the OPA test command inside the specific image registry directory where my policies exist along with the relevant unit tests. So I've already pushed this branch. All I need to do now is create the pull request and eventually merge it into the main branch once the tests have passed. All right, so you can see here that all 4 tests passed, which is exactly what we want. So I'm going to head back. All right, so once that application has been deployed to your cluster's environment and the constraint template has been synced first, creating the relevant CRD, after that, the constraint, we can then take a look at our policy, and it should be able to show us violations based on the existing Kubernetes resources, specifically the Ingress controller, which is pulling from the wrong image registry. And you can see here that there are 3 violations. We can take a look at the different resources. We have a pod, a replica set, and a deployment. If you see the message here, deployment containers are using container images from invalid or deprecated registries. So our policy enforcement is working as expected. Remember, in this case, we are specifically looking at OPA Gatekeeper's auditing functionalities. So the next time that ArgoCD attempts to sync the Ingress controller application, that synchronization attempt will actually fail because it will be blocked by Gatekeeper. So that's auditing, but now we're going to see how it works if we had the policy in place before we create the Ingress controller application. All right, now I'm going to demonstrate how policy enforcement works when the Gatekeeper policies are already in place. So the Nginx Ingress controller has not been rolled out as yet. So we shouldn't see any violations. You can see there they are 0 at this point in time. And if I come to the existing ArgoCD applications, the Nginx Ingress controller doesn't exist at this point. So what's going to happen now is I'm going to attempt to create that. And in that process, it will try to create resources that have violations. It will try to pull images from invalid registries, and in those cases, those particular resources will fail to create, and eventually it will get stuck in the synchronization loop and terminate the operation because Gatekeeper is blocking the creation of those resources because it goes against the policies that we've put in place. So another quick look at the ArgoCD application that creates the connection between the Helm chart repo for the ingress controller and our destination cluster. But remember, very important over here is that we are specifically defining that these images get pulled from the old image registry. And I'm going to create that. You can see over there, one or more objects failed to apply because of the admission webhook. And it did specify there that Gatekeeper is essentially blocking the creation of certain resources. You can see that our deployment resource is failing to create because it is trying to pull images from an invalid image registry. If I come to applications here and I go back to the policies that I have in place, remember, this shouldn't have any violations because it has completely blocked them to begin with. And the violations would only be detected in the case that these were resources that existed in the cluster. Thanks a lot for watching. Please be sure to provide feedback in the comment section below. Also, remember, we released a couple of different shorts related to the image registry update that will help you manage this entire transition or migration process. And if you're looking for policy enforcement examples, specifically with Gatekeeper or Kyverno, we have some in our EKS best practices guide.